Professor Ángel Martín Pendás. Ángel is a full professor of physical chemistry at the Department of Physical and Analytical Chemistry at the University of Oviedo, Spain. The whole his scientific career is connected with the University of Oviedo, where Ángel got his bachelor in chemistry 1988, PhD in chemistry 1982, and associated professor position. He became the full professor at 2011. His research is focused on methodological developments in theoretical and computational chemistry, particularly regarding fundamental aspects in theory of chemical bonding in real space. Ángel proposed a theory of interacting quantum atoms that provides an exact partition of the molecular energy into ionic and covalent interactions. Since 2007, Ángel is the PI of the QTCOVI group. Since 2011, he obtained big funds exceeding more than 1 million euro only for theoretical purposes, and next 6 million euros from projects in which he participated. Ángel developed great international collaborations, including Paul Papelier from Manchester, Carlo Gatti from Milan, Hernández Turillo, Professor Roja, Professor Hernández La Moneda from Mexico, Professor Sabin Contreras, Breda from Paris, Espinoza from France, Lorraine University, Cochus and Finzel from Max Planck Institute, Munoz and Cardenas from Chile, etc. Ángel supervised around 15 graduate, postgraduate, doctoral and postdoctoral students in the last 10 years. And his students hold now international academic positions in Mexico, Ireland, also positions in Spain, and are postdocs or works in private companies. Ángel is active member of theoretical chemistry community. He organized 2 international conferences in Oviedo, ESPA 2010 and ESCB 2018. He also has written a textbook together with Julia Contreras on topological approaches to chemical bonding, published by Springer last year. He very actively participates in evaluation of scientific research, serving as in different domestic and international commissions and panels. In 2019, Ángel was selected the president of the European Committee for Chemical Bonding, a non-profit society that proposes development of the theory of the chemical bond. And so, since 2019, he is an associate editor of Molecules, and since 2022, member of WOTOC board. Ángel published circa 240 papers and delivered circa 50 invited talks. His Hirsch index is 49, and his papers have now more than 10,000 citations. Today, Ángel will present a lecture entitled "Is the one particle approximation biasing our interpretation of real space chemical bonding descriptors? The cases of Laplacian and of electron density and electron localization function." Ángel, the screen is yours.
Okay, thank you so much. Well, first of all, I want to thank the organizers, Pauline and Christophe, for this very nice introduction and this invitation. It is both a pleasure and a great honor to deliver this talk today. And I have chosen a topic that might be interesting to this quantum crystallography community, and that might also sparkle some debates. Since I will be focusing on the Laplacian the electron localization function, Born maximum, etc. I will devote some minutes to present basic facts about these descriptors, although many of you will be basically familiar to them. So our community has been struggling for years to find electron density accumulation depletion descriptors. Since after later we know that these are related to the core of the concept of chemical bond. It was soon found that, for instance, deformation densities used in crystallography were very sensitive to the references that were used to build them, and this eventually led to using orbital invariant descriptors that led to the topological method. We could use, for instance, the density itself, which is quite dull because it decays very fast, as you can see here in the purple curve for the argon atom. But as soon as you multiply it by r squared, forming something like a radial density, you recover immediately the atomic shells of the system, K, L, and M. That are also found if you plot just the logarithm of the density here in this green curve for the argon atom, which shows very clearly 3 exponential patches with different exponents. You can also obtain these accumulation regions using the Laplacian that, as you know very well, just senses the difference between the value of a scalar field at a given point and the mean value of it over a neighboring domain. If we Taylor expand this difference, we find that the dominant term is related to the Laplacian, so that if the Laplacian is negative, then the value of the scalar at the point that we are interested in is larger than that average in the surrounding region. For each exponential patch, the Laplacian has a negative and a positive region, and then oscillates widely. So since we want to measure regions of accumulation, we will use in the following not the Laplacian but minus the Laplacian, which we call typically the L function. And to put it on the same scale as other descriptors, we will take the arctangent of L, which is here shown in green for the argon atom. You see the 3 shells, and also notice how the position of the maximum of the outer shell from the radial density and from the Laplacian are close to each other, but are clearly different. This is a problem that we will encounter all over the lecture. If we, on the other hand, want to study electron pair localization descriptors, we can use, for instance, the very well-known electron localization function, which is in its original formulation was based on the curvature of the Fermi hole. If we study the behavior of the probability of finding a given electron at a distance S from another reference electron with the same spin, then this probability is 0 if both electrons coincide due to Pauli principle. So if we Taylor expand this probability around the reference atom, the leading term is parabolic, and the curvature of this parabola, which is called D, is the curvature of the Fermi hole. This curvature, if small, means that the reference electron is excluding a large region of space from being used by same spin electrons, and these regions will be then invaded by opposite spin electrons, so that this is the origin of the so-called Lewis pair or the electron pair. Since the curvature of the Fermi hole is an extensive quantity depending on the number of electrons, typically we want intensive ones, and we divide this D by the curvature of a reference systems, typically the homogeneous electron gas in a single Slater determinant formulation in a system with the same density as the one that we want to study. This ratio is called the kernel of the ELF, and since low curvatures and low kernels will be associated to large pair localization regions, then we subject this quantity to a Lorentzian scaling to form the final formula of the electron localization function. This has been used for decades to find regions of electron pairing. Its attractors are related to these regions, and we immediately find them in simple molecules like this methylamine molecule, regions associated to bonds and also to lone pairs. and probably the ELF is the best way to recover the valential electron per repulsion model of Professor Gillespie and co-workers. But notice that the ELF is what it is. It is nothing more than its definition. And then care has to be taken with regions in which just one electron resides. If we have just one electron, then the per electron density is 0, the curvature of the Fermi hole is 0, and then the electron localization function will be 1. This means that, for instance, in the outer shell of the sodium atom, which has just a 3s electron, the ELF will, let's say, asymptotically go to 1. On the other hand, in the outer shell of argon with 4 alpha and 4 beta electrons, the electron localization function will decay to 0 very, very, very quickly. There are other descriptors for electron pairing. For instance, electron localizability indicator provided by Kahoot, YELI, based on the so-called omega restricted partitioning, or the localized orbital locator, which is related to the positive definite kinetic energy density and also to the electron localization function. All of them recover basically localized orbitals in regions of pair localization. Any of these descriptors, the Laplacian, the electron localization function, or the law provide different kind of information, but are based on either one electron, let's say the Laplacian, or 2 electron properties at most. The point that I want to raise is whether this mean field averaging that takes us from the n electron distribution to the 1 or 2 particle description is affecting or biasing our understanding of the electron distribution. To guess if this is so, we have to examine the full n electron probability, which we call the Born probability provided by the square of the wave function. For a 1 electron atom, let's say hydrogen in its ground state, this is a square of the wave function. And if we sample it, if we take a snapshot of the electron at different times, then we get this kind of cloud plots that can be summarized by the point in space at which the probability is maximum. This, in this case, is just the nuclear position. In the general case, what we do is to locate the 3n dimensional maxima of the square of the wave function, which is nothing but the equivalent to finding the positions of clamped nuclei under the Born-Oppenheimer approximation. This is nothing but an optimization problem that can run into several technical difficulties, which I will not enter into. And typically, a common solution to find this maxima is to sample space through quantum Monte Carlo calculations. This program was initiated many decades ago by Arman, and now it's run by others like Andreas Savin, Anthony Shemama, or Anne Luchot. If we take very simple examples, in helium, we have 2 electrons of opposite spins, so the 2 can reside at the nucleus. This is the maximum of the square of the wave function. The 3rd electron in lithium cannot be found at the nucleus because of Pauli, and then it will be found at a given distance from it. There are an infinite number of equivalent maxima which have this electron moving on the surface of a sphere. And if we add a 4th electron, then Coulomb correlation in beryllium will take these 2 electrons and dancing on the ends of a dumbbell that runs over the surface of a sphere. If we proceed with these ideas, in boron, we have 3 valence electrons in a triangle, 4 in a tetrahedron in carbon. Notice different spins with different colors. And finally, 2 interpenetrated tetrahedra that form a perfect cube in neon. Notice that there is no need for hybridization to find a tetrahedral arrangement of electrons in carbon. If we measure the distance of these maxima to the nuclei, we find that they decrease with increasing atomic number, that all these ideas are close to Linnet, our model of repulsion. And as I'm going to show, that same spin blocks are more rigid than different spin blocks. Notice also that, for instance, in neon, the 2s and the 2p electrons lie at the same distance from the nucleus. We cannot distinguish them. They are indistinguishable electrons, no different in distance to nuclei. This is the plot for the 2nd and 3rd row atoms. Lithium to carbon have already been shown. In nitrogen, we have a tetrahedron of alpha electrons capped with a beta 1. In oxygen, a tetrahedron plus a dumbbell of beta electrons, tetrahedron of alpha plus a triangle of beta, and finally 2 tetrahedra in neon. It is in this sense that opposite spin blocks are more rigid than inter-spin blocks. You can find the geometry of each spin block separately by minimizing the repulsions of the electrons lying in it, and then just put one block on top of the other and rigidly rotate one with respect to the other to find the minimum energy, the minimum repulsion energy. If we go now to the third period, we add a cube of 2s and 2p electrons, and then we repeat exactly the same structure. So I guess that Mendeleev would be quite happy with this periodicity of the electron structure that we see from this maxima. If we just take a look to the shell structure of full subshells and shells, we have these 2 electrons for beryllium, a cube for neon, 2 cubes for argon. But in krypton, the M shell is full. We have 3s, 3p, and 3d, 18 electrons, and they distribute in this quasi-spherical shape that was actually known to Thomson's back in 1904 when he studied distribution of electrons on a sphere. If we take the 9 alpha electron block, then the polyhedron that minimizes repulsion is this well-known capped square-ended prism, or if you want a tri-capped trigonal prism, if you rotate it a bit. So we have 3 layers of equilateral triangles just rotated one with respect to the other. If we now superimpose to this object another equivalent for the beta set and rigidly rotate them till we minimize repulsions, we find this structure which rotated has this shape in which 3 layers of hexagons of opposite spin also rotate to it with respect to each other are found, which is exactly this. Notice that the polyhedron related to this 9 electrons object is exactly that we find in some complexes very well known to the valence shell electron pair repulsion model. Now let's go directly to our 1 electron problem, and let's from now on assume that the Born probability maximum is a faithful representation of the electron distribution. Take a very simple example like the beryllium atom in its ground state, a single determinant 1s2 to s2. Then the electron probability distribution is the product of 2 equivalent objects for the alpha and beta electrons, since opposite spin electrons are uncorrelated. And the probability of the alpha electron set is just the square of this determinant. If we develop it, it is just the square of 1s at 1, 2s at 2, minus 2s at 1, 1s at 2. And then the maximum of this P alpha probability, since the 1s electron has a big cusp at the nucleus, will have 1 electron at the nucleus, and the other will be found at the point in space where this expression is maximized. Notice that it will not be at the point at which the 2s electron squared has its maximum, because here we have the 1s function also. So the 1s function is influencing, it is interfering where the position of the 2s maximum is, and this means that the Born maximum does not or will not coincide with those of the 1 electron picture. Actually, you can see this in beryllium very clearly. In purple, we find the square, the density of the 1s orbital. In green, the density of the 2s orbital. And in blue, the probability that we have to maximize. Notice that the maximum of this probability is definitely at a different, it is close to, but definitely at a different distance from that of the maximum of the 2s function, and a little bit closer to the nucleus. If we now take our cherished descriptors, here with points, we have the positions of the Born maximum at the single determinant level in black and the correlated level in red. In purple, the ELF, which saturates to 1 because we have an outer s electron. In blue, we have the arctangent of L, and in green, we have the LOL function. Clearly, the ELF has no maximum, it saturates, but L and LOL have 2 maxima, which are close to, but at a larger distance from the nucleus than the Born maximum. This is quite general, and if you examine several examples, we find the same structure. So in lithium, we have the Born maximum, which lies in the inter-shell region for the electron localization function, and 2 close, but definitely at larger distance, 2 close maxima for LOL and the Laplacian. If we go to neon, then now the ELF goes to 0. The 3 maxima are closer to each other, but are different from Born. And if we add 2 extra shells, then we have 3 different distances for Born maxima, and basically the same distribution for LOL and ELF. and the Laplacian. So the maxima of these are at larger distances, the same for krypton, just to give another example. In general, the position at which the ELF maximum occurs is larger than that of LOL, larger than that of L, and larger than those of the Born maximum. This is quite general, as I say. In molecules, we have several nuclei and many different local maxima of the square wave function. For instance, in dihydrogen, we find two types of maxima. In one, we have one electron at each of the hydrogen nuclei. And in the other, we have two electrons in one of the two nuclei. At the Hartree-Fock level, the probabilities of these events is the same, 50-50 percentage of the covalent, let's say, and ionic contributions, but the covalent one is more likely in the correlated description. If we proceed to further to other molecules and perform variational quantum Monte Carlo calculations, then in diboron, in its triplet ground state, we immediately see two boron atoms like the ones that we have seen before, perfectly distinguishable. This is not the only maximum that we can obtain. There are others in which we have spin excitations. For instance, in this, the rightmost boron atom is in a quartet state with the three valence electrons of the same spin. And in dicarbon, the singlet global maximum distinguishes perfectly two ground state triplet p carbon atoms. We have rotations, spin excitations, and also ionic situations. Here, the left carbon has one extra electron. It is like a nitrogen. And the rightmost carbon has an electron less and is like a boron. What we are seeing here is that the electronic structure of atoms is very well conserved in molecules, much more than we initially expected. This is this transmitted or visible in our standard descriptors? We will take a very simple example, ethane. This is the standard graph. In green, the bound critical points. And what I want to show is that in many cases, the Laplacian is a very good descriptor of the position of the Born maxima. These are the maxima of the L function of minus the Laplacian. Notice that we have one maximum at each of the atoms, and the very well-known 4 valence shell charge concentrations around the carbon atom. The positions, the distances at which these charge concentrations occur are very close to those in the isolated carbon atom and very close to each other. The Laplacian is also very similar in both cases. We can also plot an isosurface of the Laplacian, or maybe better, this type of isocontours diagrams that you are familiar with. If we now change to the electron localization function, what we find is we have just one attractor for each valence pair of electrons, and that the two attractors found in L disappear to form just one attractor at the center of the carbon-carbon bond. The same is found if you plot a LOL isosurface. What I want to show now is that it is very easy to rationalize this kind of behavior. Here I will first show the Born maximum of ethane. All the electrons are found here. Notice the spin alternation, the 4 electrons in tetrahedral coordination around the carbon atom, and below the maxima of the L function minus Laplacian, in which you can see a one-to map between the maxima of Born distribution and that of L. I'm going to examine now what happens along the carbon-carbon direction. In this plot on the left, we have one carbon at each end of the x-axis, and I have plotted the arctangent of L for the ground state triplet p carbon atom in purple. Here I just add its symmetric for the rightmost carbon. If we add them together, we have this total Laplacian, and if we compare now this Laplacian, atomic Laplacian, promolecular one, with the true Laplacian from an actual calculation, we see that the core regions are basically atomic, and that it is only in between the two maxima, so in this region, that we can find these density accumulations. Notice that the two maxima, atomic maxima, are still resolved, and that they correspond very well to the position of the two electrons in the Born maximum. So this is saying that if the bonded valence shell charge concentration are well separated, we will have distinct maxima, and no, that will not happen otherwise. That is the case for the ELF. This is the ELF of the left carbon atom. Notice that the maximum occurs close to the bond critical point. This is quite interesting. This is the ELF of the rightmost one, and surprisingly, the actual ELF of the final system is this, which is indistinguishable from them, in which the two maxima have fused together, and now we cannot resolve each of the two electrons. So in the case of the electron localization function and also in the LOL, it is the long-range character of its behavior that leads to fused basins. If we plot everything together, then we see how the L function discriminates, resolves the two electrons of a pair, but how the LOL and the L functions fuse them. It is even more interesting. Here I plot behavior of different densities along the carbon-hydrogen bond in methane. The full density, electron density is in green, the one of the core in blue, and that of the sigma carbon-hydrogen bond in purple. What we see here is that in the valence region, the density is dominated by that of the sigma bond, and then the position of the two electrons of the pair coincide extremely well with those maxima of the orbital that describes the system. So, and now if we take a look to our descriptors, then the L function, the Laplacian, discriminates both electrons, but either ELF or the LOL do not. In general, if the density of the wave function is dominated by one orbital, then bond maxima coincide with orbital maxima. But this is not always the case. And a simple example is silane. If we go to silane, now the full density is this purple curve. The core density is the blue one, and the green curve is the sigma, the density of the sigma silicon hydrogen bond. Notice that there is no maximum in the valence region here except in the hydrogen atom, and that the secondary maximum of the orbital that describes the bond is located in the core region. So if we put an electron here, it will clash by Pauli with those of the core, and then nature has found a solution for this problem, and this is pushing the two electrons of the bond towards the hydrogen region. If we plot the Laplacian, the maxima of the L function, then we find no bonded valence shell charge concentrations here, a maximum at each hydrogen atom, and then a core of formed by 4 maxima, which are counterpolarized. I will devote some minutes to this problem in a few slides. Of course, the Born maximum is ionic, so we have 2 electrons at the hydrogen atom, and the core is a simple L shell that forms a cube. The whole picture is like this. On the top diagram, we have ELF. On the medium one, we have the maxima of L, the minus Laplacian, and then we have the Born maximum. In methane, we have 4 attractors of the L for each of the carbon-hydrogen bonds, and they correspond to these 2 maxima of the L function, one at the hydrogen and one in of the valence shell charge concentration of carbon. That, of course, map in a one-to-one manner to the maxima of the Born to the Born maximum. In ammonia, this is the same for the nitrogen-hydrogen bond. But if we examine what happens with the attractor of the ELF related to the lone pair, this is mapped. It holds, of course, 2 electrons. This is mapped to a single attractor in L. So this L attractor at L attractor has 2 electrons, which are, of course, resolved in the case of the Born maximum. The same occurs for the 2 lone pairs of water. They are mapped to just 1 L maximum in the Laplacian, but they correspond to 2 different electrons in the Born maximum. Finally, the toroidal attractor of the ELF in hydrogen fluoride, which with about 6 electrons, corresponds to the degenerate critical point of the L function, and of course to 6 very well resolved electrons in the Born maximum. So just summarizing, counting from L, from the Laplacian, is typically unsuccessful. Sometimes the maxima of L have 1 electron, sometimes they have 2, but positioning them is quite successful. On the other hand, counting from ELF is more reliable because we add the 2 electrons, but positioning from the ELF is relatively unsuccessful. And of course, by construction, counting and positioning is obvious from the Born maximum. Let me just show a few examples coming from this. Very simple. First, I'm going to consider ligand-induced charge concentrations, and I'm going to establish if they are true or fake. This is related to a very old problem. The linear geometry of beryllium and magnesium halides, but the angular geometry of calcium, strontium, and barium halides. This was also a problem for Gillespie and for his model, and together with Bader years ago, they proposed these ligand-induced charge concentrations, which were actually found in the 1990 book by Bader when he examined the Laplacian of calcium hydride. In these coordination chemical reviews, he wrote that negatively charged ligands in transition metal and heavy metal molecules seek out positions of minimum charge concentration in the valence shell charge concentration of the metal atom. The same is found if we use the electron localization function. This is a paper by Gillespie, Sylvie, and others. It has given rise to very important papers like this by Martin Kaup, in which he found that departicipation or core polarization through dipole moments favor the non-VSEPR structures, while ligand repulsions and pi bonding favor the linear VSEPR structures. Even in recent years, Ria Brouwer and co-workers in the Netherlands have revitalized the extended dipolarizability model to account for the geometry of these systems. Let's start with the Born maximum of the calcium atom, which still displays 4 shells in the Laplacian. We have a core with 8 electrons, which is structured to the outer core with 8 electrons. And these two are the 4 s electrons that lie at 1.4 angstroms from the nucleus, very far. The calcium hydride molecule is clearly bent. It has a large topological charge in the hydrogens or in each of the hydrogens. And the L function has 4 maxima in the calcium region, which do not coincide with the bond directions and which are, of course, ligand opposed. So for each bond, we have a ligand opposed charge concentration. At the bond maximum, we see an ionic situation. So each hydrogen has 2 electrons, but notice that the outer cube does not show this ligand opposed structure. Actually, we find an alpha and a beta electron, an alpha and a beta electron along each calcium hydrogen direction. So from this idea, we could, in principle, think that the ligand opposed charge concentration are an artifact of the one determined expansion. What about departicipation? We can perform an NBO decomposition, and then the calcium hydrogen bond has a clear departicipation, D.0.32. And from the bond maxima, we can also isolate those in which 1 or 2 hydrogens have only 1 electron, and then the region around calcium has either 9 or 10 electrons. These lie at basically the same distance from the nucleus, and they are thus necessarily d electrons. So there is clear departicipation, and it is immediately seen from this type of analysis. Also, these 2 structures have dipole moment in the core, and this dipole moment is in agreement with this polarizability idea. What is the reason for this different behavior of the Born maximum with respect to the L? Well, in the case of a correlated description, then the 2 electrons of a pair are resolved. They cannot lie at the same point. And then we see this cube in which we have this non-ligand opposed distribution. But if we switch off correlation and go to a single determinant expansion, then we find again the 4 tetrahedron of 4 maxima, which are ligand opposed, and we also find an inner core which is counterpolarized with respect to the outer one. So in this sense, if we use a 1-particle description, if we use a single determinant approximation, then the ligand opposed model appears. But if we use a correlated one, it does not. So whether it is fake or true, it is still a matter of debate, but I just raised this idea to the audience. Of course, if we go to magnesium hydride, this is linear. We have an ionic Bohr maximum. And since the magnesium second shell is full, it does not admit extra electrons. The NBO has no departicipation at all. The maxima of L are normal. And to summarize, as it is usually the case, all available explanations are compatible among each other. Ionic compounds have the Bohr maximum a divalent metal, with the departicipation coming from the covalent electrons that fill the N-1 shell in the monoionic and neutral structures. And these monoionic and neutral structures have an atomic dipole, which is consistent with increasing polarizabilities and with the Weiss model. My final point relates to related to core polarization. This is also related to ligand-induced charge concentration, and there is a very nice paper, a relatively recent paper, in which this is just taken to the core. Here, our colleagues examined silicon chloride with and germanium chloride, for instance, via the electron localization function, and they found that in the first case, the core, the ELF core was ligand opposed, while in the second case, the outer core was directly polarized, while the inner core was counter-polarized. And they related this, let's say, alternating structure of core polarization, direct polarization, to the hardness and softness of the cores in these systems. This has been repeatedly found elsewhere, and what we find is that cores respond to valence electrons. In the case of the Bohr maximum of methane, we have the 4 valence charge concentrations in L, which correspond very beautifully to the Bohr maximum. In silane, we have already seen the, let's say, ionic structure with just the L shell forming a cube. But if we go to a single determinant approximation and switch off electron correlation, then we recover this counterpolarization and the ligand opposed description. Notice also that even in the orbital model, the 2s and 2p orbitals of these systems already display this ligand opposed polarization. In germane, the situation is different. Now the bond is less ionic and more covalent, but the outer core has 18 electrons. And it is here where I find an important difference. If we find the maxima of the L function, then we see a tetrahedron which is directly polarized, not counterpolarized, as of course it is also found in this paper. But notice that even if we go to the single determinant approximation and we switch off correlation, these 18 electrons correspond to 9 pairs. This is again the object, that polyhedron that we found with 9 electrons. And what we find in the Bohr maximum is that one of these pairs faces directly one of the ligands, but it is frustrated because we have several possibilities in which this pair oscillates between the 4 ligands. Of course, if we go to the inner core at the single determinant approximation, then we see again that this counterpolarized. Notice that in this case, the orbital picture shows no signal of direct polarization. The 2p and 3p orbitals are counterpolarized even in this germane. So the problem from this point of view is that both the density or the electron localization functions belong to the A1 representation in tetrahedral symmetry, and that this is compatible with 4 pairs, either directly or counterpolarized, but not with 9 pairs. So the direct polarization of the 4th and 5th periodic compounds that is found is related for sure to this 18 electron shell, which is considerably more complex than the 8 electron shell of the other cases. So we have geometrical frustration of the 5 pairs. Each L maximum is associated to 18 over 4 electrons, and also the larger covalency of these systems is playing a role. So in my opinion, it is not the hardness or softness of the cores of these systems, but simply that we are facing cores with different numbers of electrons that shift the system from counterpolarized to directly polarized. And with this, I will go to my conclusions. I hope that I will have convinced you that this electron counting perspective is valuable itself, that the atomic shell structure and the electronic structure itself persists in molecules, much more than expected initially, that when we build one or two particle descriptors by compacting the n-electron information, we sometimes create, sometimes hide structures, and that this is dangerous, that it is the range of the maxima of ELF or LOL or similar descriptors that lead to fusing the electrons of the pair to form a single attractor, thus recovering these kind of pairs. That if we compare Born L and ELF, we have a better description of the system, and we can understand their mutual compatibility. That ligand-induced or opposed concentrations all are compatible with Linnet-like ideas of repulsion, minimal repulsion of electrons, and that please take much care if you count electrons either from ELF or from Laplacian densities. Let me finish by thanking the Oviedo team. Without their help, this could not be possible, of course. Our funding agencies, and just an advertisement. As Paulina has said, we have just written a textbook with my long-term colleague Julia Contreras on topological approaches. It is written for advanced undergraduates and master students, and it covers the Q-time, 1 and 2 particle descriptors, weak interactions, both molecules, solids, algorithms, software, exercises with solutions, and so on. It takes a didactic approach, and I simply encourage you to ask for some copies for your academic libraries, your institutional libraries, or for your personal group libraries. And that's all. Thank you so much for your attention, and I'm happy to take questions.
Thank you very much, Angel, for this excellent lecture. And there are first questions to you. Marcin Ziemniak is asking which descriptor do you consider to be better, ELF of LED? Some sources claim that LE is superior to ELF. What's your opinion about this?
Okay, so this is my opinion. So I think that you should ask this to Miro, to Miroslav Kohut. But anyway, I will give my opinion. So ELF, the electron localization function, was developed thinking in single determinant wave functions. Then many other interpretations were found in terms of kinetic energy densities, etc. But in principle, the interpretation of ELF based on the curvature of the Fermi hole is only valid for, let's say, uncorrelated situations. What LED is doing is to provide an equivalent description to that of ELF, which is exactly the same formula in the case of single determinant approximations, but that can be immediately generalized to correlate descriptions. So if you have a correlated wave function, then definitely you should use LED. And if you have, let's say, a wave function coming from DFT, which is in the end single determinant, or Hartree-Fock, then any of the two will give you exactly the same results. So that's my idea around this.
Yeah, we have next question from George Aikering. Thank you for this very nice talk. Considering the core polarization discussion, as we have seen in the transition metals, we may also trace the inversion of the polarization patterns to the nodal structure of the orbitals. In how far does the Born analysis generally depend on the orbitals and their nodal structure? In some sense, the results appear to be orbital free to me, but on the other hand, they are based on example of Hartree-Fock calculations which employ an LCIO ansatz, I assume.
Okay, so several points here. I will start with the last part. So in principle, the Born maximum is completely orbital free. What we are showing are the results of quantum Monte Carlo calculations they are based on, to start a variational quantum Monte Carlo calculation, you need an initial wave function, and that typically is a single determinant one or one based on orbitals. You start with one, but as soon as you start a quantum Monte Carlo calculation and you add just factors to account for correlation, then the final result is explicitly correlated. So the two electrons of each pair are separated, etc. And then to what extent these depend on the initial wave function that you started with is not is something that has to be investigated. But in principle, the results are completely orbital invariant. This for the last part, and for the first part, which I will try to read again. Yes. What we have seen, and I have tried to show with very simple example, is that yes, this is related to what is the structure of the orbitals, because the structure of the orbitals is actually giving you where the nodes are, and the nodes are extremely important to locate electrons, because electrons will avoid nodal regions. So again, as I typically say in every time I talk, everything that people have done to understand the electronic structure of any system has a point of truth. So orbitals are useful, orbital invariant descriptors are useful. They are all telling you the same story. It's simply that you should take into account the points of view of others to understand better what you do. So yes, with orbitals, orbitals are everywhere, and they will be there forever, because they are useful. They are very useful. But orbitals are in a way biasing our interpretations, because as I have tried to show, at the very moment that you put into account the correlation of motions of the different electrons, the one particle picture fades away. So they are there, you will find things there, but I think that we have to go beyond.
You have already started answering the next question, which is by Guillermo Monaco. Thank you very much for the excellent presentation. What do you mean by saying that a two-electron description is biasing our interpretation of bonding? Should not the two-electron density matrix be sufficient to recover the Born maxima in some complicated manner?
Again, yes and no. So the two-particle density, and from it we can obtain the one-particle density. The two-particle density is sufficient to obtain the energy of a system, okay? But that will only, because the energy, the Hamiltonians that we typically use, the Coulombic Hamiltonians, have only the two-particle operators. So the only two-particle operator in the Hamiltonian is the electron-electron repulsion. So if we know the average, distribution of pairs of electrons, we have the energy, because we have the average electron-electron repulsion, and that's giving you the energy of the system. So to obtain the energy, yes, we just need the two-particle density. But if we want to go beyond, and chemists want to go beyond the energy, but because what we do in chemical bonding is exactly that, going beyond the energy. The energy is that given by the code, but you want to understand it. And to go beyond the energy, then you need to understand how the electrons are correlated. And the correlation of the motion of electrons is not defined only by the two-particle density. It is something that needs further other reduced density matrices. So in a way, yes, in another sense, no.
Okay. Some other people are writing now. Oh, thank you from Guillermo, and
well, that's
other thanks from Province Sadar Palpanu.
In the meantime, I have a question, Ángel.
Yeah.
Maybe a short explanation for those who are not very much familiar with many kinds of quantum chemical calculations.
Yeah, sure.
Can you say a few words about quantum Monte Carlo approach? So this is orbital free, basis set free approach, or?
Again, yes and no. So if you could solve directly the quantum Monte Carlo equations, let's say you would need nothing. So it is completely orbital free. But there is a problem in quantum, a practical problem. You need to know where the nodes are, so where the wave function is zero, because it is not obvious at all how to obtain these nodal surfaces from quantum Monte Carlo calculations directly. So then practically you start from an approximation, you start from a wave function that is obtained from some other method, and then you refine it. And there are many variants of quantum Monte Carlo in which you just strictly have the same nodes as those in the original wave function, or if you do some other variants, then you just modify them to go to the final, let's say, exact solution. But with quantum Monte Carlo, you in principle approach the exact solution of the Schrödinger equation.
Mm-hmm.
And how much it is dependent on so anyway, you have to have some kind of starting basis set, right? In which you represent your wave function.
Yes, you start. You let's say that for practitioners, you start doing a Gaussian calculation or something like that. Or if you are in a solid, there's also quantum Monte Carlo for solid. You do a plane wave calculation, and then that's your starting point. If the calculation converges correctly and the statistics, because one of the biggest problems of quantum Monte Carlo is the statistics of the problem. It is just a statistical average what you get by sampling and sampling and sampling. If the statistics is good enough, then the results are not very dependent on the starting point. If the statistics is bad, then they are, of course.
And this Born searching for the Born maxima and the whole procedure, can it be applied to the wave function from the standard quantum calculations?
Yes, for sure. You can just take a wave function and look where the maxima of its square lies. The problem is that at least as far as I know, there are no codes that do that. So people who have been searching for this have done it using quantum Monte Carlo because it is easier. So imagine that the problem is, let's say it's a formidable problem from a computational point of view, because there are millions or billions of maxima which are equivalent by symmetry, and then let's say sorting out everything is not immediate. And when you do quantum Monte Carlo calculations, the electrons are already at given positions in space with these walkers that you use, and that is favoring the finding of these maxima. So the use of QMC is just because it is usually done that way, but any wave function could be used to find this maxima, no problem at all.
Mm-hmm. Two people among others, Hans Bert, are writing now questions. Yes, Hans Bert, for a lay like me, what is the answer to your title question? Is there a clear answer?
No, there's not a clear answer. I was just posing a question because I just want you to know, want this community to know, that maybe we are using things and we are extracting conclusions that are just artifacts from what we are doing. So when we talk about, let's say, core polarizations or ligand opposed charge concentrations, we are talking about the density. But if we now change the density by electrons, then we can do this kind of reasoning, which is wrong. So the idea that the density has this charge opposed concentration, sure. But that does it mean that the electrons are accumulated there? And maybe the answer to that is no. So the average, the electron density, which is an average, a one particle average, so is the probability of finding electrons, but it is not giving you information about how the other electrons are distributed. So when you collapse, when you just do a section of something which is very complex and you transform it into a one particle object, then you can find an answer which you extrapolate to what the full set of electrons are doing. And maybe that is not the case. So maybe the electrons, if you look at where each electron is in the molecule at each time, if you could perform, let's say, less than attosecond snapshot of your molecule, you would not find that, very likely. It is the average that gives you that result. So maybe some of our ideas are biased. To what extent is something that I think funny and interesting to find in the future, of course.
But then it's also, you know, a matter of the property of your molecule, because some properties are like long life kind of properties, and others are attosecond kind of.
For sure.
Events.
So of course. So there is no doubt. So in the density, you see this, but and I'm not doubting that that is an artifact of X-rays or of calculations. So the density has those features. But those features are an average of situations which are probably not equivalent to what you think of that. So I immediately imagine with these ligand opposed charge concentrations that the electrons do not accumulate in the bond region, but that they go the other way around. But as you have seen, there is still accumulation of electrons in the bonding region. It is just when you average out and perform the density that you see these maxima appearing in the opposite directions, which, by the way, coincide with the points where the orbitals have these secondary maxima. So maybe we are going back to orbitals. I don't know. It's something that I still have to think about it. For me, it's really interesting. I'm very interested in these things at this moment because it's shocking in a way.
So you are basically saying that with attosecond experiments, we would see different picture?
Very likely. So it as you say, depends on the time scale of your experiment.
We have the next question on chat. Can you please comment on the utilization of quantum Monte Carlo calculations for the calculation of Curie point for small organic ferroelectric system?
Well, the answer here is very easy. I don't know. So sorry for this, but I'm not an expert on magnetic systems at all. So I don't know how you could use Monte Carlo calculations for this. No.
Paulina mentioned this attospectroscopy. You mentioned in your lecture that at certain moment, coarse electrons respond to valence electrons. Do you think that this kind of effects could be confirmed experimentally, for example, by XPS or techniques?
Again, I'm not an experimentalist, so I just throw these ideas to the community. So I would like to see. This is the point where some experimentalists could come in and say, okay, maybe with this I could find some observable that could be related to what you are saying or not. I am not an experimentalist. Sorry, but I don't know.
There is
another one.
Paulina, can you read it?
Thanks a lot for the talk. Yeah, from Alfonso Gallo, once again. I have the feeling this analysis is a cleaner analysis than usual, since it consists of directly exploring a wave function. Would you say that it's theoretically simpler or more straight than LF or LE or whatever L is escaping from orbital picture, a way of simplifying the electronic structure study?
Let's see. Let's say for a theoretician, it is close. This is close to the dream of a theoretician, in the sense that if you could find this kind of maxima or of structures easily, very quickly for any system, then you could explore really how the correlations between the movements of electrons in the system are. But that is not the case. So this is expensive. It is not for every system, and they cannot, and they will probably never be found experimentally. So the experiments, science is experiment. What we are doing is just theory to prove that experiments are correct, or the other way around. So I don't find that ELF, LEL, or whatever will be surpassed by this kind of analysis in a near future. So for me, they are very close to what an organic chemist, let's say, expects. So you can see electrons moving from one place to the other. You can see how an electron jumps in a reaction. That is immediate from this kind of analysis, and you can see the electrons in space. So it is very clean in that sense, but it is very far from experiments at this moment. So it is not simplifying the electronic structure study. Maybe it's doing the other way around, but it can provide some ideas that other people may try to look after in the experiments. So that is what you have to do, not.
And you have shown us like some kind of optimized structures, or like atoms and molecules being in the equilibrium kind of state.
Yeah.
So it's, do you expecting any difference if you do some kind of study along the dissociation curve or something?
Yes, I've done them already. So you see, you find what you expect. So let's say you start with what I have shown. Maybe I hope that it has become clear after all, is that the atoms do not change so much when they form molecules. So that the structure that the electrons display in the atoms is basically the one that you find in molecules, although there are some slight differences. So sometimes electrons rotate, move in along bound directions, but you still see the shells, you still see the electrons at points in space. When you dissociate, or when you put two atoms to form a molecule, what you see is the contrary. So you have the atomic structure, and then the electrons slightly move till they accommodate to that final structure. So it's really a nice exercise, and you see a movie and you see the electrons just slightly moving to accommodate to the final situations, nothing else.
Okay, as I do not see more questions nor comments. Thank you, Ángel, for
thank you so much.
Excellent.
It's been a pleasure
And discussion, very interesting discussion.